Hi, everyone. So yes, the title of this talk is Everything I Know About React I Learned from Twitter. You're going to find out exactly what that means in a second. But first of all, I'm Jen. I work at a company called The Wing, based out of NYC. We build co-working spaces that are geared towards women. I'm a front-end architect there, so I run the front end. And I'm also a co-organizer of a meetup called Use React NYC. I put out some stickers on the table, so if you see little New York React stickers, that's us. If you want to reach me online, my handle is girlcode, girl with a U, so definitely reach me out on Twitter. Now, when I'm not doing my day-to-day job, I like to think of myself as a React detective. And today I want to share with you some of my detective sleuthing. And as all great detective stories, we're going to begin with a tweet from Dan Abramov. So I talk about React a lot at conferences, at meetups, at dinner parties. I am very fun. I do a lot of research for these talks. So a lot of detective-like digging for clues. And this strange thing started happening to me when I was searching for answers. Because this tweet, I didn't see it on my timeline. And I follow Dan, of course. I think if you're into React and you're on Twitter, you follow Dan. But you're not going to see every tweet. But what's interesting is when I started searching for something, a normal Google search, that's when this tweet popped up. And it's exactly the answer that I was looking for. And this sort of kept happening to me. So at the time, I was trying to write a talk about concurrent React. And the team had just introduced this term at ReactConf at the time. So I wasn't exactly sure what that term meant. Was it referring to the concept of async React, or was it referring to the reconciler that's behind that? And turns out it's an umbrella term, so yes to all of the above. But I actually couldn't find this information elsewhere. It was just a really new term. And this just kept happening to me. I would need an answer for a talk about React, and the answer would actually be in a tweet from the core team, and I would find it in a Google search. And it happened again and again and again, and then eventually, my desktop looked like this. And it's not just the tweets, because I'm having to connect all the pieces together. So I have tabs open with the documentation, and then these tweets are flooding my desktop, and then suddenly I'm in the React repo reading a comment on a pull request from 2 years ago, and my brain is like, it's a lot. And now I have this folder of Dan Abramov tweets on my desktop, which is very normal, and I realize I could literally give a talk on these tweets. So welcome to that talk. We're going to be looking at some of the tweets from the core team, some pull request comments, and some source code. And in the end, we're going to understand React's internals at least a little better. OK, so we're going to start where all React internal introductions start, with the virtual DOM, or in this case, the hope that we retire this term. So the basic idea of the virtual DOM is this. React takes your application and generates a tree structure that is a virtual representation of the DOM. And when the application is updated, it then compares a new tree to the previous tree to diff the updates and change the DOM. But the VDOM doesn't have much to do with the DOM at all. VDOM started as a really useful concept to explain how reconciliation worked, that whole process of understanding what's changed and what needs to be updated. But reconciliation is actually independent from the renderer. So that might be the DOM for web applications, but it also might be React Native. And virtual DOM also has this connotation that the DOM is the problem somehow, that React is solving for a slow DOM. But that's not what's happening. React is solving for building applications that are maintainable and fast enough. And reconciliation is part of that. It's reducing the work to commit to the DOM, but it doesn't make React faster than the DOM. React actually has more work to do than the DOM. It has to reconcile an application, and the DOM doesn't need to. That's why the core team has spent years building a new reconciler nicknamed Fiber. But first, we're going to look at the old reconciler, known as the Stack Reconciler. Okay, so we write JSX like this, which Babel then transpiles into calls to React.createElement. These actually return to us React elements like this. So when you call the render method of a component, you're ultimately calling React.createElement and getting back a React element or a tree of React elements. Now, React elements are immutable objects describing a component instance or element node. So for each element or component in your application, there's a corresponding React element to describe it. And this is all still true with Fiber. None of this part has changed. What's changed is that the reconciler is no longer recursively traversing your application to render each component and create a React element tree. That recursive process actually blocked the main thread, and it couldn't be interrupted. The Fiber reconciler doesn't use recursion, and it doesn't block the main thread. It can pause its work to yield to the main thread and then resume when the thread is free. But that's not the only feature of Fiber, because pausing reconciliation is the mechanism behind suspense. We can pause and wait until some information we need arrives. And it's also how priority levels can be implemented. So we're going to be able to allow for a higher priority update to come in and take precedence over a lower priority update. And this just wasn't possible with the Stack Reconciler and recursion. But it is possible with Fiber, because its architecture re-implements the stack. And that's why recursion isn't needed or wanted in Fiber. And this can feel really confusing at first. So don't be concerned if this doesn't make sense right away. Honestly, Sebastian's tweets almost never make sense right away. But in the immortal words of Dan, I want you to remember that if React is a horse, then Fiber is a horse on acid. Fiber is trippy, y'all. And I want to note that what Dan's referring to here is Fiber with a capital F. That's the reconciler. But there's also a Fiber with a lowercase f. So what you're looking at here is a Fiber. And to avoid confusion, when I say Fiber from now on, I am explicitly referring to this data structure. Unlike React elements, Fibers are mutable. So React elements are meant to describe what you want to see on the screen, but Fibers keep track of the current inputs and the past inputs and outputs of a node in the tree. So all Fibers are going to contain a tag key that corresponds to the Fiber type. So for example, if you have a class component, it's going to be of the class component type. And if you have a function component, its tag is going to be function component. Fibers link to their children, their siblings, and their parents, also known as their return. So similar to React elements, Fibers form a tree structure. We can traverse that tree using a while loop and a parent-first, depth-first traversal algorithm. So this is how we actually traverse without recursion. And if you look in the React source code, you're going to see a lot of while loops. By the way, if you want to explore Fibers in your own application or someone else's, you can do so using the React internal instance key. So here I am on Dan's awesome blog, Overreacted, if you've ever read it. He goes very in-depth on things, but it's very, very useful. And you can see that I'm grabbing the toggle element and viewing its Fiber. And you can see how much information is on that Fiber. I'm not going to be covering all of the information that are on the Fibers because it is a lot that they have to keep track of, but we'll go over some of the core parts of it. Now, I was really curious about where Fibers come from, when they're created, and the best way to understand source code is with a debugger and some breakpoints. So here's a simple application that I made. It's just a box that when you click on it, it's going to toggle its background color from blue to tomato. Tomato is the best color. And then here's the code for the component. So it's just extending React component. And when you click on the div, we're going to toggle the color with set state. I'm not using hooks in this, and that's because I'm going to teach you some of the basics of how this works the old way. And hopefully, if you're interested, you can dive in and learn hooks on your own. And then this is the code to render the application. And you'll notice that I'm using unstable create root. So this actually ups this application into async or concurrent rendering. Now, this is unstable, so we don't use it yet. But I want to get a sense of how the fibers get started and get created in concurrent mode first. So please don't use it. And then this is what the application's fiber tree is going to look like. And you can notice the one-way and the two-way relationships. Now, the first time our application renders, these fibers don't exist. So we call React DOM.unstable create root, and we're going to pass in the node that we want our application to render to. Now, that's going to call new React root. And in that constructor, it's going to call create fiber root, which then calls create host root fiber. And that function creates the first fiber, which is tagged as the host root fiber. And this fiber's job is just to host the fiber tree. The host root fiber is returned to create fiber root, which then creates a root object and assigns the host root fiber to its current key. The root is returned to React root's constructor, where it's assigned to the internal root key. And now our React root is returned and assigned to the root variable. So that's everything that just happened in this one line right here. So now we have an internal root saved on the React root class, and its current key points to the host root fiber. So before we even start rendering our application, we actually have a fiber in place, but it's the host root fiber. So now we can actually start rendering our application. We're going to call root.render here, and remember that calling this is actually calling React root.renders method, which consumes the output of React.createElement, which is a React element. And that method is going to grab the internal root and provide it and the element to schedule root update, which is going to save that element to an update object, and then pass that update to enqueueUpdate function. Now, enqueueUpdate is going to add that update to a list of state updates on the fiber called the update queue. And this was going to be processed at a later time to update the state. So at some point, we're actually going to see that React element from the render method added to this fiber state, but not quite yet. enqueueUpdate is done with its work, so now schedule root update is going to call another function called schedule work. Now, this is an oversimplification because while I've talked about concurrent mode, I'm not going to go into a lot of the specifics on it. It would take more time than I have here. And also, it's still a work in progress that the team is currently figuring out some issues with. So what schedule work is essentially going to do here is it's going to set a timer with a callback. And that callback is going to perform the actual work. So once that's done, schedule root update is also done. And then our render call is complete. So that's everything that happened in these lines right here. Now we're going to wait for that timer to expire, and the callback that schedule work put in place is going to be called. And this is, by the way, very, very short. You're not waiting like a long time for this at all. When the timer is done, the callback that it's going to call is the perform work function, which calls render root, which calls create work in progress, and it's going to pass in the current fiber. Now, create work in progress is going to assign the current fiber's alternate as the work in progress. The alternate is a pooled version of a fiber. So instead of continuously allocating and then destroying fiber objects, an initialized fiber object is kept at the alternate key. And this is known as double buffering. So there's a current fiber that represents the current flushed state of the fiber, and a work in progress fiber, which is free to be modified. So information is read from the current fiber, and information is written to the work in progress fiber. And when changes to the work in progress fiber are complete, it's going to swap places with the current fiber. The work in progress becomes the current, and the current is now available to be reused for work. And this is why we don't see an alternate being set yet. You're going to see in a second. This is, by the way, I think this is like really, really cool. But on your application's initial render, the alternate is not set. You're going to see alternate null here, right? So we only have the one fiber currently, and then later it's going to create the second alternate to all of these fibers. So basically each element in your application has its own sort of fiber, and each of that fiber is going to have an alternate. Now, the exception to this is the host root. So it does get an alternate on the initial render. So we have a current fiber, that's the host root, but we can't actually write to the current, so we need to create a work in progress fiber that we're actually going to start writing to. So we're going to create another fiber using the information from the current one. We're essentially, at this point, making just a copy of it. And then we're going to assign it as the alternate. So now the host root has a current and an alternate, and the alternate is going to become our work in progress. As we create the rest of fibers in our tree, remember that they're currently not going to have an alternate. They're just going to be coming from this current alternate. So work in progress is now done. And now work in progress actually gets assigned as our next unit of work. And that means we're now going to actually enter the work loop. This is actually where React is going to start to perform the work on our fibers. And this is the actual work loop. It's called whenever React needs to render the application. And while there is work available, it's going to perform that work. And the units of work, they're always fiber nodes. So every time there's a unit of work, that unit of work corresponds to a fiber node in the fiber tree, and that's what it's going to do work on. So the first one we're actually going to work on is the host root. So work loop is going to call perform unit of work with the unit of work, which is our host root. And then it's going to pass that work to a function called begin work. Now, begin work is going to determine what type of work actually needs to be done based off of that fiber's tag. So in this case, the tag is that it's a host root. Since host root is special and it's meant just to host the rest of the fibers, it has its own work that needs to be done. And you actually are going to call a specific function for it called update host root. Now, we're actually going to process that update queue that we were talking about earlier. So our new state is actually going to be the element that we received from root.render. And we're going to save that state on the fiber's memoized state key. So memoized state is the current state, the most recently updated state. Whenever the update queue is processed, the final state is going to be stored here. So we're keeping track of the fiber state. When we return to update host root, we're going to assign that element from the state as the next child. And then we're going to pass the fiber's child, which is currently null, and the next child, which is the React element, to reconcile child fibers. Now, currently, because host root doesn't have a child, its child is null, reconcile child fibers is going to see that the child fiber is null, but that a next child has been provided. And so it's going to create the work in progress as child from that element. So now the host root is actually going to get its own child fiber, which is the div element. And then we're going to return that child down the stack. And then that child is actually what gets assigned as the next unit of work. So remember, we created a child fiber, we returned it down the stack, and now we assign it as the next unit of work, which always is a fiber node. And the work loop is going to evaluate this, and it's going to see that there's more work to be done. So it's going to start up again. Same as before, perform unit of work, begin work, except this time, because begin work is responsible for deciding what type of work to do, it's going to call a different function called update host component. So when you have something like a div or an h1, something that's a native DOM element, the tag for that is a host component. So in this case, it's a div. And then what we're going to do here is just a little bit different. So begin work, because it's tag-specific work, and since it's called this update host component, we know that we need to look at the pending props of that fiber. So we're going to grab the children from those pending props. So pending props are just props that are waiting to be applied. And of course, children is a key, so we can grab it and we can use that. And so we're going to reconcile the child, which is still currently null for this fiber, and the next child, which is going to be props.children, and we're going to decide what we need to do there. Now, this is a little bit different, because in our fiber tree, you'll notice that the div actually has 2 children. So what we're actually getting back here is an array of children. So we actually have to call a special function called reconcile children array. So what this is going to do is it's going to take the first child from the array, and it's going to go ahead and create a fiber for that child. And then it's going to take all subsequent children and attach them as siblings to that fiber. So we get an array of children. We just go ahead with creating all of the relationships between them. So they're all siblings. We go ahead and create each fiber and mark it as siblings to each other. Then we're going to actually return just the first child down the stack, and then assign it as the next unit of work. And so we enter the work loop again, because again, we still have work to do. Same as before, work loop, perform unit, begin work. Another host component, because this is an H1, reconcile child fibers, except the H1 actually doesn't have a child. So it gets a little bit different here. Normally what we have been doing is we get the child and then we pass it back down the stack as the next unit of work. This is going to be a little bit different because it's actually null. So we're actually going to pass null down the stack. We don't actually have a child that we need to reconcile here at all. And then the next unit of work is actually null now. Now, it gets caught before you exit the work loop. So you're still in the work loop, and it knows that the next unit of work is null. So what this says to the work loop is actually what we now need to do is we need to complete all of our units of work. So we consider this branch now to be complete. And so we're actually going to call complete work, which is very similar to begin work. So it's going to do tag-specific work to complete that fiber node on the tree. And then it's going to return the next unit of work. Now, the next unit of work, because there were no children, it's either going to be the fiber's sibling or the fiber's parent. So if this didn't have a sibling, it would just return the parent and we would go up. A very simple application, one line. But since this actually does have a sibling, we're going to return the sibling down the tree. And it's going to be assigned as the next unit of work. So the work loop is going to start all over again with this new sibling, and this is how we go down one branch and then over and down again. So we've started completion on the H1, we move over to another branch, and we're going to go down that as well. So we're going to begin and complete the work until the entire tree is complete. So at this point, when everything in the tree is complete, that's when the work loop is actually finally going to stop. And there's just no more work for it to do. So this is also when we're safe to actually commit this work and flush it to the screen. So we're going to assign the work in progress fiber as the root.current. And so remember that we're going to switch places. So the work in progress becomes the current now becomes the work in progress fiber. So they switch. Now, everything that we just went over when we were building up the fiber tree is part of the render phase. So there's a couple of phases. There's the render phase, pre-commit phase, and the commit phase. Now, in the render phase, and this is very important, that is the phase that you can actually interrupt. It's the asynchronous part. But that's only in async or concurrent rendering, which, as I mentioned, the team is still working on and is not available yet. But when it is available, it's the phase that can be interrupted and yield to a host environment if needed. Now, the commit phase, however, cannot be interrupted. The commit phase needs to be deterministic. So it's OK to have interruptions when you're in the process of building up or updating the fiber tree. That's the whole point of what the fiber reconciler is supposed to be doing, because it knows where it is in the stack. So it can pause, it can rewind work and replay work. You can also throw away work. But the commit That's when you're actually seeing things on screen, and so you don't want your users to see a little bit of changed UI here and a little bit of changed UI there. That really needs to be consistent and uninterruptible. So this is one of the points of what the team is working on now, and this is actually why this work is quite difficult, is because you're allowing updates to come in and change things, but you actually need to resolve to a final state so that the user sees something consistent. And so that's a lot of the work that they're doing right now on scheduling, is how do we make sure that everything is always consistent? And I didn't yield to the host environment in this example of building up the fiber tree. But what would happen is we would yield to the host environment every 16 milliseconds or so. Now, Sophie has this really wonderful comment with more specifics about this. And sorry, I'm not going to read this whole thing out, but my slides will be online later. But she's also writing here about how the React core team is working with the Google Chrome team and the W3C on a new feature called isInputPending. And that will make their work with scheduling and priority updates a little bit easier. And what Sophie is also talking about in this post is starvation. So because concurrent rendering allows for interruptions and priorities, there's a possibility that a lower priority update will continuously be interrupted by a higher priority update. And remember, I said they need to resolve to a final state at some point. So you can't ignore the lower priority update for forever. You need to be able to integrate it after the higher priority updates are done. In other words, React is going to starve. It's not going to be able to actually flush the resolved state to the screen. So what the team is doing right now is essentially it will switch over to synchronous mode if it has a timeout. So if you have a low priority update, it's going to come with a timing mechanism on it that once that expires, concurrent rendering is going to stop being concurrent. It'll be synchronous, and it'll flush everything to the DOM, and this will prevent starvation. So now we're going to look at a set state update. So when you call set state, you're actually calling set state on the component's prototype. And this is actually calling enqueue set state with the fiber that needs to be updated and the update. Now, this gets added to the fiber's update queue. And then enqueue state is going to schedule the work again. So again, a timer is going to have a callback function. And now we're just kind of done waiting for that timer to resolve. And when it resolves, it is once again perform work. We're going to call render root. And again, we are switching the fibers here. So the current alternate becomes our work in progress to make sure that we are writing to the correct one and we leave the current flush state alone. Yes. So again, it's going to be assigned as the next unit of work. And we're going to enter the work loop again. But remember that this time, the component and its child are the only ones that have actually changed. So nothing else actually needs to be updated here. It's just that component and that div. So the same process we've already seen before. Perform unit of work. We're going to begin the work. And then this is a little bit different. Now, this check for old props and new props actually does happen in that initial phase when you're building up the fiber tree. But the check doesn't matter there because there are no old props to compare to the new props. So it's always going to return false, and we don't have anything going on here. But with an update, this might return true. So the old props might match the new props. And so in that case, we're going to bail out of this work because there's nothing for us to do. So if the old props don't match the new props, we know there's actually work for us to do. And what's going to happen here is basically the div and the h1, well, their old props and their new props actually are the same. So we can bail out of all of the work with them. So we're just going to return their children and start up the work loop again. And we're going to bail out of the work for the div, and we're going to bail out of the work for the h1. Nothing's changed there. And then we enter the work loop with the component that's actually changed. So the same process as before. So React has, in its reconciliation, ways of skipping work that it knows it doesn't need to do. So pretty quick win. Other words, in recursion, you couldn't really skip. You still had to call as you were recursively going down the tree. Now, same process as before, perform unit of work, begin work. Now we're going to call update class component, because this is a class component. So remember, begin work decides what type of tag-specific work we need to do. This is a class component, so that's what we're going to call. And then we're going to request that we update the class's instance. And this is also where getDerivedStateFromProps happens. And this is also where we check for should component update, because we also might need to bail out in case of those. But in this case, we don't. They actually are different. They have changes, and we didn't say should component update false. So we're going to process the update queue to get the new state. And that state is going to be saved as the Fiverr's new memoized state, its most recently updated state. And then we're also going to update the instance's state so that it has the freshest, newest state. And then we're going to call instance.render. So remember that this is going to call render on the component, and it's going to give back to us a React element. So that actually gives us back our next child. And we're going to pass the current child and the next child to reconcile child fibers. So this time we actually did have a previous child, and now we also have our new next child. Now, what this is going to do is it's going to set the fibers tag, effect tag. And what this means is the effect tag is actually telling you what type of work needs to be done. So it might be a placement or a deletion, and in this case, it's an update. So anything like that becomes an effect tag, so they know what to do later. Now, in the initial render, this actually also happened. It's just that every single effect tag in that was a placement, because it was the first time it was all being pushed to the screen, and that's just not very interesting. So now we're going to return that work in progress child, the new React element that we got down the stack. And now I'm going to skip ahead because I'm not going to make you go through the work loop again and again and again. So we're going to skip ahead to when we've completed all of this work. So now we can commit this work, and what's going to happen is whatever renderer you've chosen is going to look at the effect tag and decide what needs to be done. So because this is a web application, React DOM is responsible for looking at the effect tag for an update and deciding how to handle that in the DOM. But if you were React Native, you would have a different renderer looking at this and deciding what it needed to do with that update tag. Same for placements and deletions and so on. So that's when we're actually going to see the screen on the device actually update, no matter what your renderer is. So remember that this is actually independent from the DOM. You know, I've put references to DOM tags in here, but really, it's more like this. It's just, you know, fibers that are all connected in a tree, and it really doesn't matter whether these are DOM nodes or it's meant for React Native. And these fibers track their input and output, you know, their state, their props, their children. But again, none of this has anything to do with the DOM. And this is not a virtual representation of the DOM. The VDOM does not exist. It's not a thing. Now, this is also the re-implementation of the stack that Sebastian's kind of confusing tweet was talking about. Because, you know, a program's execution is tracked using the call stack. And when a function is executed, a new stack frame is going to be added to the stack. And that stack frame represents work that is performed by that function. So Fiber is a re-implementation of the stack. It's specialized for React components, but it is a re-implementation of the stack. You can think of a single fiber as a virtualized stack frame. And I think this is super cool. And I really didn't understand this at first until I went through the whole process of debugging this and saw how much information the fibers were tracking and what they were doing with it. And also seeing how removed this actually is from the renderer, like the DOM or React Native. Just understanding what the fiber's tracking, this was super interesting to me. And this also really helped me understand why recursion is not going to work for the reconciler. Because if we were to recurse down this tree and then pause, we lose a lot of context. And we need that context if we're going to be able to pause and come back to our work. So by re-implementing the stack, we're not losing everything, the inputs and outputs, and where we are in the stack at that specific time. It's actually a lot of work to try and do that with recursion. Now, somebody asked me recently if learning all of this really changed how I wrote React. Well, actually, they didn't ask me this recently. They asked me this a while ago. So I first gave this talk back in March of this year. And my answer at that time was just a flat-out no. Because the truth is, you don't need to know all of this to be able to use React. That's one of the things I really love about it. If you're interested, you can dive in, but you really don't need to learn all of this. However, I will say that since that time, with the release of hooks, understanding a bit more about how fibers are built up and how they save information has helped me understand hooks, use effect, and things like that. So I get a little bit clearer of an understanding of how hooks are used, how they're saved to different fibers, and why the call order matters. So that actually did sort of help me with hooks. But other words, you don't really need to know any of this. I think I definitely became a better engineer diving into all of this, because this is extremely different from what I do on a day-to-day basis. Looking at how a framework is built and the code involved in that and what they're solving for on the React core team is so very different from the UI work that I do every day. I really enjoyed that part of it. And I also understood a lot more of the complications of what the team is dealing with. So I went over like a snippet, a bare minimum of like what's going on here. It would take me many more hours to explain to you a lot about scheduling or what's happening with the hooks. But, I hope that you've maybe been inspired a little bit to dig in to this source code if you're interested. You don't need to know it, but it is really fascinating. And just remember that if it doesn't make sense at first, that's really okay, because, Dan and I told you that fiber is trippy. It's a horse on acid, y'all. So, thank you. Oh, and I'm not going to do Q&A, but please, you can come talk to me at the front.
Well, thank you very much, Jen. So we've got another talk starting in a couple of minutes. We've got you're going to have some difficult decisions to make coming up for the rest of the day. I think there's lots happening. Here we've got the awesome Martin Split, developer advocate, webmaster trends analyst at Google. He's going to be talking technical SEO. In the other room, we've got local superstar Mark Dalgleish from Melb.js, going to be talking about designing components. So make your decision and make it correctly. Back in 2.